When we look at the standard cosmological makeup, split between baryons, dark matter, and dark energy, we see a model that accurately predicts the universe's expansion history and the acoustic peaks of the cosmic microwave background. This accuracy relies on assigning completely independent, unobserved physical sectors to handle different epochs of cosmic time: an inflaton field for the beginning, a cold dark matter particle for structure, and a cosmological constant for late-stage expansion. As precision cosmology pushes the limits of observational data, we are finding cracks between these isolated sectors. Early universe inference and late universe distance measurements currently disagree on the rate of expansion, creating the Hubble tension. Simultaneously, late-time matter clustering fails to match early predictions, resulting in the S8 structure growth tension. These persistent discrepancies indicate a structural failure in our baseline equations, rather than simple measurement errors. This raises a specific physical question. What if these independent dark sectors are actually distinct temporal and energetic regimes of a single dynamical medium? Dynamic vacuum field theory defines the vacuum as a physical, dynamical medium. This field is defined by a single complex scalar equation, mapping both amplitude and phase. The amplitude, ρ, controls the vacuum's stiffness, its inertia, and its overall gravitational response. The phase angle, theta, dictates the coherence, the causal time ordering, and the interaction structure of the field. Observational cosmology requires specific behaviors, like negative pressure to drive acceleration, or cold clustering to form galaxies. We can derive these exact behaviors directly from vacuum dynamics, without requiring new fundamental particles. In standard cosmology, solving the Friedmann equations backward yields an infinite density state as the scale factor approaches zero. The mathematics break down into a singularity. Dynamic vacuum field theory replaces the singularity with a mathematically finite, yet highly unstable initial configuration, where the vacuum amplitude sits near zero. The behavior of this amplitude is governed by a specific potential equation, visualized here as a potential well with a steep peak descending into stable circular valleys. At the exact origin, the effective mass squared is negative. This creates a tachyonic instability, forcing the vacuum state to rapidly cascade down the curve toward the stable minima. As it descends, this tachyonic phase exponentially amplifies long-wavelength vacuum modes. The result is a scale-invariant primordial power spectrum, generated over a finite range. The standard model requires an entirely independent inflaton field to achieve this exact mathematical outcome. By treating the vacuum as a dynamic field, both the mathematical singularity and the need for artificial inflation are replaced by a natural tachyonic emergence. The data from the CMB and large-scale structure require a cold clustering gravitational sector, regardless of whether it is composed of particles. Following the tachyonic phase, rapid expansion causes the vacuum field's phase coherence to break down. As the field cools, the phase vectors rotate and misalign, creating localized points of topological lock through a mechanism called phase winding. This winding condenses into a distinct, stable vacuum defect with a fixed mass, acting as a powerful source of gravity. Initially, these defects are produced with a wide momentum distribution. However, they are immediately filtered through topological locking and continuous reabsorption by the surrounding vacuum. This filtering precisely suppresses the high momentum tail, satisfying the strict conditions for a cold relic distribution long before recombination occurs. The deep gravitational wells required to seed galaxies are sourced directly by cold vacuum defect relics, completely eliminating the need for an unknown dark matter particle. Because these defects emerge from a continuous field, rather than perfectly collisionless particles, they retain a slight residual velocity dispersion. This minor velocity dispersion directly impacts how cosmic structure forms and clusters across billions of years. This is a log-log chart comparing the expected matter power spectra between standard cosmology and dynamic vacuum field theory. On the left side, at large linear scales, the vacuum defects cluster exactly like standard dark matter, producing identical overlapping predictions. But on the far right, at much smaller scales, the residual velocity dispersion causes the vacuum transfer function to drop below 1, creating a mild, scale-dependent suppression. This exact high-frequency suppression directly influences the S8 parameter, which measures late-time matter clustering. This bar chart compares the S8 parameter values predicted by each model. The predicted S8 value naturally drops below the high baseline established by Planck, aligning neatly with the lower values actually observed by weak lensing surveys. Furthermore, late-time cosmic acceleration occurs naturally as the entire vacuum equation of states smoothly relaxes toward equilibrium, removing the need for a static cosmological constant. Modern cosmological tensions regarding structure growth and expansion rates appear as the exact mathematical signatures of a dynamic vacuum. Any alternative cosmology must pass a strict standard of scientific rigor. A single fixed parameter set must run through a standard Einstein-Boltzmann solver and simultaneously explain all datasets. The highest hurdle for any model is reproducing the acoustic peaks of the cosmic microwave background to extreme precision. This line graph maps the expected temperature and isotropy spectrum of the CMB under this framework. The theory successfully aligns with the first two peaks, but predicts a slight systemic modulation specifically localized at the third acoustic peak. Standard cosmology assumes the CMB's lensing amplitude depends solely on integrated gravitational potential. However, dynamic vacuum field theory predicts vacuum stress contributes directly to this lensing. This creates a mathematically correlated deviation between the exact lensing amplitude and that third peak's height. This specific correlated shift offers a clear, falsifiable target for the theory against standard models in upcoming data from the DESI and LSST surveys. Cosmic evolution follows a continuous sequence. Vacuum disequilibrium triggers tachyonic instability, condenses into topological defects, sources structure, and eventually relaxes into late-time acceleration. This continuous evolution simplifies the heavily fragmented multi-particle epochs currently used to patch standard models together. If upcoming survey data confirms the single-parameter correlations predicted by the Boltzmann solver, our understanding of the universe must undergo a structural update. This dynamical vacuum serves as the primary agent of cosmic evolution.